Okay, so everything miraculously seems to work today. So let me get back to the last thing that I was discussing last time. So I was reviewing these different ways in which you can look at when you extract an accessible term or a collection of accessible terms. In the different ways in which you can view what remains from that extraction. And as I was saying, this have all of these things have different meanings with respect to the linguistic interpretation. But basically, there are three things that you can do. One is to, if this is the accessible term that you want to extract, you can contract it, shrink it to its root vertex and keep some form of labeling for the kind of structure that you have extracted. And as I said, we're just going to write the label in this form, but it doesn't mean that you have to remember the old structure, which would create an infinite set of labels. You just have to remember the syntactic feature that tells you the role that the structure had. Or you can make a cut and keep this non-branching vertex here. That again is a way of remembering that there was something that you have moved that was in that position. And this is sort of what usually is referred to as a trace in linguistics, but it does not necessarily have to be labeled. It just reminds you that that's the place from which you have extracted something. And then there is the unique binary tree that's determined by this, which is the one where you don't keep any sign of the structure that you have extracted. And as I was saying last time, you can think of this first form of quotient as being, in a sense, the one that gets interpreted in the sense that when you do a semantic parsing of your resulting structure, the fact that something has moved and what type of role it played in the place it was moved from is something that you do interpret, so you do keep track of that. And on the other hand, the one where everything disappears, any trace of the structure has been moved disappears, is the one that actually goes to the externalization, where you only externalize once the structure that has been moved, not a second time. And this intermediate step is sort of relating the two. And so, as I was explaining last time, if you take these different ways of defining what is left from the extraction of an accessible term, these have slightly different algebraic structures of the product. And I was mentioned the fact that for this intermediate, this intermediate stage, you get something which is a co-module over a Hopf algebra of trees, where the trees are allowed to have non-branching vertices in addition to binary vertices. And the comodule is the one of the actual, fully binary trees. And I also mentioned last time that if you take this contraction, coproduct, one where you keep the root vertex with the labeling, then you get a co-algebra. And it's not, it can fail to be a Hopf algebra in degree 0 because now you have several things, because the single leaves with a label by a lexical item or syntactic feature are now in degree 0 with respect to the grading for which this is graded algebra and bialgebra, which is grading by edges rather than grading by leaves. Then so this only makes you lose a globally defined antipode, which is not problematic because, as we'll see, there's nothing that really strictly depends on the antipode. But you do have an antipode modulo this ideal where you will just identify all these generators of degree 0 together. So that's the algebraic structure that this kind of quotient term determines. It's a bialgebra, and the Hopf algebra modulo this ideal. And yeah, so this was just a comment on the labeling set. And yeah, so that's where I stopped last time. What happens in terms of this deletion quotient. This is the one that, as we were saying, kind of goes to the externalization, where you lose all traces of where you have extracted structure. So, this so the accessible the part that you extract is always just a collection of accessible terms, but now the part that you construct, since you're taking the maximal binary rooted tree with leaves decorated by your set, so 0, you can have examples where you don't have anything. Like, for example, if I start with a tree like this and I make an admissible cut that cuts both of these edges, it is an admissible cut, but then I'll be left on the right side with just the root vertex by itself. But the root vertex is unlabeled, so it doesn't exist in my category or in my class of binary rooted trees with leaves labeled by nothing. So it means that in a case like that, well, the maximal tree available that's contained is just the empty one. So you will get cases like that where you have, but of course this means that there's some countings of the terms that you get that is going to affect what happens when you apply the coproduct more repeatedly, when you want to check the co-associativity of the coproduct. And in fact, if you use this form of the coproduct, you see that like the list of terms that you get, if you apply it twice in one order or the other, the kind of terms that you get will be the list of terms will be the same, but they actually don't necessarily match with multiplicities on the two sides. And in fact, one can, in a sense, try to correct for that. I'll explain it in a moment by introducing some kind of, multiplicities assigned to some weights that assign certain multiplicities to vertices and edges, and that compensates for the different counting. So this is the kind of thing that can happen. So suppose that I'm starting with a tree like this, and I take the coproduct in two different ways. So this is just the one that keeps the nodes that are unbranching. And this is the one that takes the maximal fully binary tree that's determined by this one. So if I perform this cut first, so this part falls off, and what I'm left with now would be just yes, I'm gonna have. Yeah, that's right. So this is the part. This is the part that falls off, right? The one that is on the left side of the coproduct. And now what I have on the right side, the maximal tree is just a leaf that's decorated by gamma, and the choices that I have now for making a second cut, which would be, so if I'm computing this coproduct, it means that I am first doing one cut, and then I'm doing the second cut in the part that has fallen off from the first cut. So I can do the second cut, I can do it in two ways. Yeah. Okay. And if I have the other kind of product, I'm now left with, I keep the unbranching node here, and again, if I do this counting, I'm still placing the second cut in the structure that fall off, and I got two possibilities here, and so in this case, the counting of all the possible terms will match, since the unique binary tree that's generated by this is the same that you will get with those. But if I do my first cut here, for example, then, and I do my second cut now on the part that remains. So this is not, if I want to do it in the opposite order, then this would become my first cut, and this was going to be my second cut, right? Because it will be the one on the part that remains. But now, in this case, I still have like possibilities to. So here I have the only remaining part would be just this beta gamma, because this unbranching vertex disappears here. So I only have one place where I can place this cut here. And if I keep this, and now I have two possible places where to place my cut here. So I get a term that is the same, but it gets counted twice here and gets counted only once in the other side.
Why can't you cut down? Why can't you cut the edge together?
Right, so let's say that I place my, so I'm computing this part of the coproduct, right? So the second cut, I have to place it in the part that remains, not in the part that has fallen off. So let's say that my first cut is here, right? So the part that remains in this case is just this, but in this case, the part that remains is this. There's this non-branching. And so when I make my second cut, here I have, well, of course, there's also the possibility of cutting this other leg, but that's the same in all cases. But if I cut this leg, there's one extra possibility in one case, and there's one less possibility in the other case. So it is like saying that this edge here is kind of weighting 2 with respect to here, because so you can introduce weights on the edges that will sort of remember that the two edges have actually gone together when you make this identification. And so this is you can project this here by contracting one of the two edges, and so you have to attach a weight to the remaining one. So you can kind of follow there's a few possibilities, like another things that gives you problems, as I mentioned, is if you make an accessible cut, an admissible cut that cuts two edges under the same root, because then the root becomes an empty tree on the other side. So there's some mismatch of counting, which one has to take into consideration. So here's just a little digression. There's what kind of algebraic structure is this? If you do this kind of keep into consideration this kind of mismatch of counting in the co-associativity relation. Well, it kind of reminiscent of something that is known in the theory of Hopf algebras, but it's not the same thing. So there is something that's called the quasi-Hopf algebra. So these were introduced by Drinfeld to model quantum groups, the formations of Lie groups as symmetries of quantum spaces. And in that setting, the co-associativity relation of a Hopf algebra is corrected by conjugating by an invertible element in this triple product of H. So usually these Hopf algebras are not commutative, and these elements would have to satisfy a certain relation with the coproduct, which is this pentagon identity. However, so here we have something different, which is not conjugating by an element of the algebra itself, which would be trivial in this case, but it is actually conjugating by an endomorphism of the algebra, which is some assignment of multiplicities. And in fact, it's an endomorphism, it's not an automorphism. So you should really write it like this rather than just conjugating. And yeah, so I don't know what kind of algebraic structure this is, whether there's something interesting about it, to say or not, but this is what happens. I mean, I should just mention that this slight failure of the co-associativity, in a sense, is not so important, because this kind of quotient that one takes, where you just reduce to the binary tree, is just what goes to externalization. So all the structure building part has already been done at that point, and the co-associativity is really helpful if you want to iterate the coproduct map, and also once you don't have to do that, then it's the fact that you have this failure of the coassociativity is not support. Okay, so these are these different forms. So this is the quick summary, right? So you have if you take your binary forest, no planar binary forest with the union as disjoint union as product, and this contraction of the product, it is a Hopf algebra. This is a bi-algebra, and the Hopf algebra modulo is ideal. If you take this other co-product and you allow the non-branching vertices, then it's a Hopf algebra, and the space that you want then becomes a co-module over this Hopf algebra. And if you do this deletion, the product, then it has this correction to the coassociativity. This sort of not quasi-Hopf algebra, but something like that. Okay, so I'm gonna just talk about the Hopf algebra workspaces, and essentially what I mean by that is this whole package of these different related structures. Okay, so by the way, there is these different forms of coproduct for trees and forests have already occur in the literature on Hopf algebras. And for example, there's a paper of like Premi Fardeman and Dominic Manchon that actually discusses in relation to combinatorics and numerical analysis and algorithms and numerical analysis, some of these same type of algebras that occur here. So these are actually well-known objects in the theory of algebras. And of course, as I said, there are various projection maps that relate these different quotients, and the different products are related. So they all have the same term on the left channel, and the right ones are related by these projection maps. Okay, so this is like all the preliminary algebraic structures that underlying the actual object of interest, which is this merge operation that acts on workspaces. So I'm going to define that now. So the way that it's defined in this most recent version of minimalism in the linguistic literature, it's as a collection of operators that are parameterized by the choice of two syntactic objects. So those are like the kind of structure that you want to act on. So it's going to tell you like what do you search for in the workspace that you want to act on. And so given a workspace, which is a binary rooted forest with no planar structure assigned, this operator will look for copies of these two chosen syntactic objects among all the accessible terms in the workspace. And if it locates matching terms, then it forms a new structure using these matching terms. And the components where these matching terms are coming from are replaced by the corresponding quotients where which corresponds to what in linguistics is called the cancellation of the deeper copy. And the remaining components that are not affected, they just remain unchanged in the new workspace. Okay. So this is the way this is described. And so if we want to just write it out, in terms of the structure that we just described, we can write these operations as a composition. So you can think of it this way. So you first use the coproduct in your Hopf algebra of workspaces to produce the entire list of all the accessible terms that you can act on. And then you have a delta function that locates only the term that you actually want to use in this whole list of possibilities. And this B is this grafting operator that takes a forest and hands the entire forest to a common root. So a priori, you have this for any arity, so any number of components. But because you're going to be selecting a term that only has two components, then you act on it by forming a binary structure with those two components. And then you use the product to reassemble the new workspace together. So that's the structure. So of course, this is just giving you a map that takes a basis element to a basis element, and then you extend by linearity. So it's a linear map on this space of forest. So I just want to mention that there's various instances where maps of this form occur, and so this grafting operator in combination to product and coproduct of Hopf algebra, they occur already mentioned that in these combinatorial Dyson-Schwinger equations of quantum field theory, but also in general, this I'll say something about it more a bit later today. Maps of this form on a Hopf algebra, they generally they provided that they satisfy some properties, they actually are maps that have been studied as Hopf algebra Markov chains. So this, as we'll see, is in fact a case of these Hopf algebra Markov chains. So this indeed will, and yeah, in general, those look something like this. You have a coproduct, then you have some kind of linear map that acts on the pieces of the coproduct, and then you reassemble them together with the product. So the simplest such thing is where you have only the coproduct followed by the product. So that kind of splits in all possible ways, things into two pieces and then reassembles them using the product. So you get a sum of, monomials that are coming from the decompositions. And for example, these are used, it's one of the most studied examples of these Hopf algebra Markov chains. They're used, for example, to study shuffling, because shuffle product is an example of a Hopf algebra product. And so you can formulate certain combinatorial problems in terms of Markov chains using this formulas. So that's where this kind of form of this map exists. Yes.
Yeah, no, I was just wondering, is there some kind of operatic formulation with this Markov chain story? I know there's a shuffle.
Yes, I believe so. I mean, there's a few papers that have looked at these Hopf algebra Markov chains. Basically, first is Diaconis and one of his students, Amy Chan. I think her thesis was on these Hopf algebra Markov chains. And they look especially at these shuffle product examples, and so I think, of course, algebras and operands, they're very, so I don't remember if they actually explicitly discuss the opera.
Because I remember there was some story about generalizations of the notion of opera that precisely had to do with this shuffling.
That's right. So I don't know if this directly related, this has been directly related to that or not, but yeah, that's indeed that. But yeah, just wanted to mention that it's a form of this map that is very natural in several different contexts, and here it just describes this list of properties that I've listed a moment ago. Okay, so the thing is that if one writes it like this, which follows, formalizes this list of this description of the action, and it turns out that you have several possibilities of what happens here, right? So about it, this is what it does. You have a workspace. The new workspace is going to have a new structure that's built from matching terms, or as is in print, that you find somewhere among the accessible terms. And then you have some components that get where you cancel the deeper copy, whatever portion you're taking, and then you have the remaining component that stay what they are. And of course, what this looks like can vary depending on where these accessible terms are. I mean, they could be entire components, or they could be subcomponents, two distinct accessible terms inside the same component, or it could be two accessible terms inside another component. So there are a few possibilities, and these are gone, under different names in the linguistic literature: external merge, internal merge, sideward merge, and so on. And of course, here, I'm writing just generically coproduct here, but as I was discussing before, you have the option of choosing which coproduct you want to use, and this, of course, will depend on where you are in terms of you wanted the structure to map to the syntax semantic interface or to externalization, and the relation is just through these projection maps that I described before. Okay, so, well, let me just say that, okay, this operation that selects the matching terms is really just a delta function. So what it means in particular is that it's looking in the left channel of the coproduct for a term that only has this as the extracted term, and whatever else is in the right channel. So it's looking for among, so you have this whole very long list of terms in your coproduct, but this is zooming in on only one of them, and it's zooming in on only one that has this particular choice of of a forest with two components in the left channel. In particular, this means that a priori you can act in parallel with several of these merge operations. Each one of them will be looking for a different term in your coproduct. And of course, if you don't have matching terms, then you just sense everything to zero, which means that you're trying to act with the wrong thing on the wrong place, and you should start again with something else. Yeah. So, okay. Okay, so let's look, what are the different cases of merge that you have. So external merge is the case where you pick two different components, just full components or connected components of the workspace, and you combine those together and you leave everything else as it is. And internal merge is the one where you extract a component and you merge it with its own remaining piece. This requires a little bit more explanation, as I will say in a moment, because a priori these two things are in two different places. Right? So, but I'll come back to this in a moment. And the sideward merge is just when you extract two things so it has different cases. You either extract two accessible terms of two different components, or you extract an accessible term and an entire component, or you extract two accessible terms inside the same component. And all of these go under usually the terminology of sideward merge in linguistics. So, of course, the question is, do we have too many forms of merge? and the problem is that the answer is yes. This gives you too many forms of merge. And part of the reason why it's too many forms of merge is because it's known that some of these sideward merge operations gives rise to constructions that are not syntactically viable. And so you want to kind of have some good reason for killing off some of these forms of merge. So, okay. So the idea is that there's some kind of reason why some of these terms are dominant terms with respect to other ones. So if you're kind of acting by all of this possible transformation, you think of this as being like some kind of dynamical system that's acting on your space of possible workspaces, but some of these operations are dominant terms with respect to others with respect to some kind of cost function, then you are likely to be seeing mostly some of these primary operations which are supposed to be just external and internal merge, and the other ones would be negligible, at least in the long term, that you have this action. So the idea is that it's formulated as part of what the model should include, that there is some kind of energy function, cost function that makes sideward merge more costly with respect to external and internal merge. And of course, it should be something that's very kind of naturally defined in terms. So you don't want, of course, you can always cook up some cost function that does exactly what you want. But I mean, that's sort of cheating. So you would like to a priori have some reasonably defined cost function that will, as a result, do this. And also there's like other kind of constraints, which are called go under the name. So this goes usually under the name of minimal search. And there's also other kind of constraints that we try to formulate, which is usually in the literature go under the name of minimal yield or resource restriction. So we're trying to put reasonable constraints on how these operations work. Yes.
This cost function, is it just a more mathematical version of like some possibilities?
So I'll tell you in a moment exactly
okay.
how one can define that. So we'll see. So but let me first just explain an example. What are the things that you want to keep before we decide how to kill off the other ones? So the first thing you want to keep is external merge. And so a simple example, right, is so you have a workspace, has a bunch of lexical items. Some of them are already maybe into some partial form structure. And this external merge just takes two components and combines them together. So if I write it out in terms of this coproduct, and matching of terms, grafting and product, you have two components. So you start out with a forest that has two components. So you have just the case where you have everything and nothing, or nothing and everything, and then one component and the other, and then the terms where you actually extract accessible terms from the components. So this is the primitive part of the coproduct. I mean, this is the primitive part of the coproduct of F, but I mean, this is the part where the trees themselves are primitive. And then these are the parts that extract accessible terms from the trees. And so in this case, the term that does the matching of the two syntactic objects are gonna zoom in on the term that has the two matching terms in the left channel of the coproduct. And so here it actually comes directly from this primitive part of the coproduct. And there's nothing else left because, well, there was nothing else in the workspace. Otherwise, there will be some other stuff left. And so the thing with this is that the external merge always uses only the primitive part of the coproduct. I mean, the part in which the trees are primitive. And you only select a term where you have two components of the workspace in the left channel of the coproduct, and you merge those two. And whatever else, the other components are in there, and they remain as they are, and they're put back into the workspace by the product at the end. So this the only terms that gets selected is this, and then the grafting puts together the new structure, and then the new workspace only has one component at the end. Okay, so this is a sort of example of external merge. So what about internal merge then? Okay, preliminary. So as I said, the internal merge requires a bit more of discussion, because you're trying to put together a part that you extracted with a part that remains. So there's one thing that you can do. You have formally, you have also an empty tree, right? Which is the unit for the product. And you can merge something to the empty tree, but of course this would just give you the same tree. You don't have anything else to hang it to. So it's And so this means that your magma of syntactic objects is, you can extend it to a unit on magma with this formal unit, which is the empty tree. So I just want to make a kind of side remark here that most of the algebraic structures that you encounter in, so this is like algebra below the level of groups, right? So you're normally as a mathematician, usually your knowledge of algebra starts here and goes on from here. But actually, this is like what exists below the level of groups. And of course, magma is the simplest thing. So this magma of syntactic objects, it just relies on the simplest possible level of algebraic structure below the level of groups. And then, of course, if you impose associativity, you go to semi-group. If you require that there's an identity, you go to monoid. And if you require that there's inversibility, you go to groups. But of course, you can add a unit to a magma and go to a unit of magma, and then require associativity or require the invertibility. And you have these other stuff. So quasi groups and loops are something that actually comes up in algebraic geometry. You have these Moufang loops that have to do with cubic surfaces and algebraic structures like that. But in the world of linguistics, you're usually going this half of the picture. And of course, it just continues. You get semi-rings and all this kind of other kind of structure will always tend to be on this side of the algebraic world. And that's also a reason why a lot of linguistics, it happens that several linguistics departments, they have their own abstract algebra class, because the abstract algebra classes of mathematicians, they completely ignore this world. So it's you have all these structural results for semi-groups, semi-rings, monoids, and all this stuff that mathematicians usually don't care about at all. Okay. Anyway, so you have this particular merge with the empty set that you can use. But so what does that do? If you try to incorporate also this kind of merge operations, or one of the two objects is this formal unit of the magma syntactic objects, then this is simply taking out so if the other term matches some accessible term, the result of this operation is that the new workspace is going to simply have a copy of the accessible term extracted and placed into the workspace, and a copy of the remaining term with the deletion of the deeper copy also placed in the workspace. So it kind of breaks apart and places the two pieces of the decomposition as new elements in the workspace. And this is, in the linguistic papers, and you see this described as the fact that internal merge creates a copy of a substructure in the workspace. And this is exactly the operation that does that. And then once that is available, you can apply an external merge and merge these two structures together. And so if you view it like this, you can think of the internal merge as being this composite operation of this term and the external merge. And so in a way, however, this idea that, so you write it as this composition, right, of two successive external merges, one of them with the empty set. But so in some sense, this idea that it's a composite operation, in fact, it's a little well, not entirely correct, in the sense that, as we'll see, in terms of these constraints that you have, the point is that if you try to separate out this operation on its own, it will violate several constraints. So it really kind of exists in this combined form, but it doesn't necessarily exist on its own. So it's kind of like a virtual particle that has the wrong invariance, but when it exists in combination with something else, it's fine. So, okay, one can kind of ask this question for why am I sort of why am I insisting on doing it this way? Like, why am I saying that I always merge only things that are in the left channel of the coproduct? So I'm doing this merge the empty set to move something from the right channel to the left channel of the coproduct, right? So that I can merge that. So why don't I just try to define my merge by saying I take something from the left channel and the right channel and I merge them together. After all, for external merge, that would work too, because there's going to be some term that has the two components that I want to merge, one of them on one side and one of them on the other side. So I could just say, I pick that and I pick that and I merge them together. So why do I want to only move everything to the left and then merge? Well, so one reason is this, that if I want to merge something that's on the left side and the right side of the coproduct, now I have a forest for which I'm taking, which is my workspace, for which I'm taking out all the accessible term. Usually I expect to have a lot of things, right, on the two sides, a lot of other things on the two sides of the coproduct, because there's usually going to be a lot of other stuff in the workspace which I'm not using at that particular step of my computation. And so I have to be able to keep an indexing of which are the things that I want to use and which are not at each step, which means that I have to keep some co-indexing between something that's on one side and something that's on the other side among several components to know which one I'm supposed to merge. And I mean, this is not, I mean, whereas if I can just say, okay, I pick a term of the coproduct that has two things on the left-hand side and I merge them together, right? I don't care, which one is which. And this avoids, there's in the linguistics model, people always try to avoid having to have some keeping track of indexing of structures in different places, because in a sense, how do you do that? You need some kind of memory. So it's like you need to keep a track of some memory of previous operations to know what is where, which you don't want to do for this kind of Markovian type hypothesis. So this is the reason why it's I think it's preferable, and it seems to be more closely describing what people want to have. The fact that describing internal merge in terms of these two operations, rather than trying to define it in a single step by merging two sides of the coproduct together. Okay, so here's the same kind of the same example as before. Example of internal merge. Let's start with the same. Now we have a workspace that has a single structure in it that's already formed. I mean, internal merge is the one that's responsible for movement of transformation of sentences. So we start with a workspace that has a structure already formed, and we extract. So first extract something, and then combine it with the second step of the external merge. So we want to extract this substructure and then recombine it together. Now there's you can use the fact that merging with the empty set doesn't do anything. So in this case, there's no other component, right? Also, this first operation just produces these two separate terms. I'm writing the quotient term without the trace. So the case with the binary remaining binary tree, and so the merge would have the uniform sentence. Of course, the point is that if you in terms of interpretation, you actually know that there is a structure that has been moved, so there's a trace of where the structure originally was. Okay, so I mean, this example is sort of kind of trivial, and there's okay. But I mean, well, I'll talk about some slightly more interesting example a bit later before. So by the way, here, of course, I've been writing the trees as in the form in which English sentences would appear, but of course the trees are really non-planar, so it's just the relation between the elements that is important. Yes, I mean the structural relation. So, by the way, a kind of analogy, right? The internal merge kind of looks a lot, or so conceptually looks similar to the successor function of arithmetic. If you think of the von Neumann construction of the natural numbers, so it's in a sense the same idea that you do when you form internal merge, except that now you take the entire set as a component that you merge with itself. So no, the next, like you extract the entire X and you merge it itself to form the next pattern. And the other difference is, of course, that you have a unary first step, not a binary. It's not entirely binary, unlike the internal merge. So no, sometimes if you hear some of the talks that Norm gives on this stuff, because sometimes okay, internal merge looks almost like arithmetic and not quite. That's that's what it means. But okay. Okay, so now we know which are the things that you want to keep, and let's see how we get rid of the other ones. So we want to introduce some kind of cost function, right? That's gonna somehow, with respect to which these external and internal merge are going to be the most cost-effective terms in the. So the way that this idea of minimal search is described when you read the papers is it just says that it should be less expensive to, so this is okay if I'm making a search for my matching terms in the workspace. So of course you can say the first thing that I search for is like I look what components I have and I look at whether two of these components match the term that I'm looking for. In which case, I do external merge. So that's fine. I mean, that's but then if you don't find two components, then what do you search for next? What is the easiest search that you can do? And then it's usually presented like this. Well, the next easiest thing is that I find one component and then I search for something inside that component rather than somewhere else, right? To match with this. So this is kind of a little puzzling if you think of it that way, right? Because if I just say it like this, you could sort of argue that, for example, suppose that my workspace just has these two components in it, and I'm searching for two matching terms. So the first term I find it, and it's this entire big component here, and then I have to say where do I search for the second one? The second one is a tree of this shape. So I actually have it in two places. I could decide, I could find, which one do I find first, right? Or which one am I most likely to find? And so by the argument that I just said, I'm trying to convince you that it'd be easier to locate this one, which is very deep down, this very big component, rather than locating this one, which is very near the top of this very small component. And this seems a bit unconvincing because you say, okay, here I have to really of course it's inside the component that I've already found, but it's not like I have to search to other. I mean, if I have a workspace that's extremely large, then of course I could argue that yes, searching inside the component that I've already found is easier than searching elsewhere. But I mean, if I have an example like this, why is this the case? Okay. Well, I mean, so I was puzzled by this for a bit, but there is actually a reasonable explanation for this. The point is that when you form the coproduct or to have your list of accessible terms, there are two things you do, right? You extract the accessible term and you take a quotient of the remaining one. And now, I mean, it's reasonable to say that both of these operations have some cost. So you have a cost for the extraction of something, and you have a cost for the taking the quotient of something else. And then you assemble together. So this will give a weight to the two terms that you have in product that's related to the cost of this extraction and quotient. And then when you merge two things with certain weights, then the merge structure will also acquire a weight that depends on this. So that's the kind of idea of how one can construct a cost function, right? That's related to the operations of product and coproduct that I have. Okay, so let's say that, you know, if I want to say how costly it is to extract a substructure, then it makes sense to say that, no, if I'm trying to look for it very deep down into a tree, it's a more expensive, you know, operation than if I'm just searching near the top of the tree. And so, okay, so I can say, you know, I decide that the cost is dependent on the distance of my accessible term from the root of the tree. So I can give to an accessible term a weight that is, let's say the sum to this amount, which is my cost. So the weight is epsilon to the cost that it takes to extract this accessible term. But then what happens with the quotient term? I mean, the quotient term should go the other way around, right? Because if I am taking a quotient, like, you know, if I go back to this example, if I have this very big tree and I'm modifying it by shrinking this very small piece to a single point, this doesn't differ very much from where it was. So this should be like a low cost operation. Whereas if I'm modifying the tree if I change my tree a lot, then, you know, that should be a higher cost operation. So one can, you know, assume that these two costs are kind of inversely proportional to each other. You know, they extracting something that's very deep, you know, costs more, but, you know, contracting something that's very deep costs proportionately less. Yes.
Sorry, I'm just thinking. In your picture before, in both cases, you were at the lowest point, right? Even though the second one had just less layers.
Depth, yeah.
So I'm not sure I see why it's more costly to push, well, to shrink the one on the right and the one on the left.
Well, in a sense, I'm thinking in terms of like how different the resulting tree will look from the one that you start with. I mean, in a sense, if I'm you know, shrinking or deleting or cutting something that's very deep down in a much larger tree, then, you know, I can say that, you know, what remains of the tree is much more similar to what I had to begin with than, you know, if I shrink something that's very near the top, because then what I'm left with of the tree has changed a lot with respect to what I had to begin with.
But so is the idea that cost should be dictated by the percentage of difference between the two?
Yeah, in a sense, I mean, it's of course you want to make a choice of cost function, right? That is reasonable in some sense.
I see. Yeah.
So, you know, so here, well, the idea is to say, yes, I mean, I can think that, you know, my cost is reflecting the fact of how much I'm modifying the tree.
Compared to its initial form,
But,
rather than
yeah,
like in
that-
absolute.
That's right, rather than in absolute term, but compared to what it was before I make this operation.
Is the cost, or I guess is the importance of a part of a tree, is that depend only on the depth or also like the structure of below that part of the tree?
Right, so you could refine your notional cost by also taking into account something that has to do with the actual structure of the tree that you're removing. I think the simplest choice is to just say like how deep it is. So we're saying, okay, if one just uses the depth as a proxy for like how you know large. I mean, these are you know binary trees, so you know the depth is also in some sense telling you where you know how different is what is left, right, with respect to what you get. And so, okay, so you can. So let's just make this choice that is simply based on assuming that these two costs are sort of you know, inversely proportional to each other, or these two weights of, you know, inversely proportional to each other. And yes.
Yeah, sorry, just one last question. If I have like, say, a tree with like two very, very long branches and then one very short branch, and the pattern you're identifying is on the very short branch. Then we
Well,
just-
the trees are not, what do you mean by long? I mean, because.
Oh,
the-
like,
The trees are not metric right here. There's no
Ah.
length associated to the edges.
I'm saying, say, for example, you just have a binary tree and one is much, like, one branch leads
Yeah,
to
have a
something much
lot
deeper
more,
than
has
the other.
much more depth.
And you're identifying the pattern on the right.
Yeah, that's true, but
Uh.
that was still, I mean, that was still, in a sense, modify the structure of the tree a lot, right? Because.
Oh, you're
Uh,
saying, okay, you're saying.
Yeah.
Okay, I understand. Okay.
Of course, this is kind of related to her question, right? You can make like a more, maybe a more sophisticated way, which also accounts for like the shape of the accessible terms that you are, that you are, yeah. Say a little bit more about, some more refined countings, but for now, I'm just making like the simplest count, which is where they are located, and, So if you just want to use this basic counting of where they are located, then you can take this as being a choice of cost function that reflects some reasonable distinction. And then, of course, if you have multiple extractions, the cost add. And if you have two components that have certain weights and you merge them together, then the weight is the sum of the two. So, and if you have several compositions, then also the costs will add with each operation. So you can just make this assumption about constructing a possible reasonable cost function. And so if you make this choice, then it turns out that the only two operations that are actually zero cost with respect to this cost function are these external and internal merge, and the other sideward merge operations have a higher cost. Which means that if you now you have all the terms weighted by this this parameter epsilon to some power, if you take the limit when epsilon goes to zero, then only these internal and external merge remain, and all the other terms disappear. So, as I said, there's another way in which one can think about differentiating between these various type of merge operations by putting in some constraints of some form. And so this is based on trying to identify what properties of the workspace change when you apply one of these merge operations. Like, for example, if I do external merge, clearly the number of connected components of the workspace goes down because two components are merged together as one. And with the other forms, it's a bit more complicated, but you can, again, try to identify some reasonable constraints that one can consider. So this is what called minimal yield, which is based on two different constraints balanced together in the minimal possible form. So the two different constraints. One is that you want the number of connected components to not increase. And this is just because you're trying to build a structure that kind of converges to the idea of these merged derivations is that you start with a loose bunch of lexical items, so you start combining them into structures, then you want to end up with a single formed structure. So, and of course, there are some steps where you might not change the number of components, for example, because you're doing movement on some structure, so you're not merging it with other structures, you're just merging it with itself. But so the number of components sometimes may stay the same, but you don't want it to increase. You don't want things that diverge by creating infinite, increasingly large workspaces. And the other is that you want no loss of syntactic information, which in a sense means that if the number of accessible terms, the accessible terms should not disappear. So the number of accessible terms should not decrease. And so you can put these two constraints: number of components should not increase, and number of accessible terms should not decrease. And then you can look at the minimal balance between these two, which is the case where component, the combined, so the sum of both the components and the accessible terms, which if you want are like all the accessible terms of the workspace, including single components viewed as available material, so the entire available material for calculation, only it increases by a single step. So in a sense, I'll come back to this in a moment, but this fact that you want this to increase is saying that when you want your creation of structure to have like a more complexity, right, than the structure you start with. Sense. And so even though the number of components itself is not increasing, but the number of accessible terms is increasing enough to make your complexity of available thing be actually increasing. Okay, so now how this behave, if we want to look at the effects on number of accessible terms and number of components, the counting of accessible terms now does depend on how you form this quotient structure, because the accessible terms depend on internal vertices of the tree. So, depending if you're taking this quotient that contracts everything to a single leaf with the root vertex of the extracted part as a new leaf, or if you're taking the quotient that only takes the maximal binary tree determined by that, these are going to have different number of accessible terms. Because, for example, that new leaf is an accessible term itself, which is not there in the other case, and also you are shrinking one edge by you're doing some edge contraction to get the maximal binary tree that's determined by this quotient, and that also reduces the number of accessible terms. So if the number of if you merge two different trees, then it's always the case that the number of accessible terms just grows by 2, because the two vertices are now, the roots are not accessible terms themselves, but the two roots now become internal vertices. So the number of accessible terms goes up by 2. And the number of components goes down. So number of components goes down by 1 type, because they're built together. So this is a minus sign. And if you instead now want to extract a subterm, and if you do this deletion, and then the number of accessible term is reduced by 2 with respect to, so it doesn't quite split into the 2 parts, because this part is actually loses two accessible terms. One because of because of this cancellation of because of the cutting of the edge, so it loses the root, the part that goes into the root here, but it loses another one because of the edge contraction. And whereas if you take the one where you just contract, then the accessible term only loses 1, but not. Okay, so these are the various countings up to possible typos. They are the various countings for how the accessible terms and the number of components behave. So if you do this, then you see that the external and internal merge, well, of course, depending on which quotient you take, have certain behavior with respect to this counting. And the external, but basically external and internal merge are fine with these constraints. And the one that would be the merge with the empty set, if you take it on its own, would violate these constraints, but in combination as internal merge doesn't. And the other forms of merge, they all more or less are ruled out just by these constraints. The only exception is where you extract. So it's this kind of sideward merge, which it's a bit strange. So you're extracting something from one component, but you're merging it with another component. And that doesn't distinguish between, because the counting of accessible terms and components is actually the same as if you were merging it with its own component. So this remains undistinguishable from internal merge just by discounting, but the other ones are eliminated. So if you want to do something that's a little more, keeps into account a little better the structure of the terms that you are extracting, okay, instead of just doing this counting of no loss of accessible terms and no increase of components, you can try to introduce some kind of some proxy for measuring the fact that you would like to be going towards structures with more complexity than the ones that you start from. And so rather than measuring just the distance from the root, you can measure the size of your term in terms of the number of leaves, which gives you, now something that's also taking into account the actual size of the terms that you're moving or extracting. And so now you can say, how do I want to say that I'm going towards structure with higher complexity? So I want to make sure, so if I look at my components and let's say I identify my components with where the root vertex is. And then I look in the new workspace where all the root vertices of the previous workspace have ended up, in which components they've ended up. And I would like them to go into something which is of higher complexity than the one that they started with, or at least not of lower complexity. So a lot of them will remain what they are, and some of them are merged with something else. But no, I would like each of them to go to something that's not losing in complexity measuring this way in terms of their size or the degree in the terms in the alpha. And so external merge is fine because it just adding the degrees. Internal merge is fine because it's just the same of the component that you start with. But if you take the other form, submerge, you will always have some term. So if I end up with a piece of my new workspace that is just a quotient, not merged to anything else, just the quotient itself. This means that the root vertex of this tree is ended up in a component that has lost something. So it's going to something that is good complexity is decreased. So I can say that, okay, maybe you can just do like a more refined counting rather than just the depth at which you pick the workspaces, which has to do with this kind of measuring of how things behave in terms of their size. And then you will have that only the external and internal merge satisfy this no complexities. Okay, so the other next thing that is one of the wish lists of the linguistic model is why is merge a binary operation? Or why do you only have binary merge, or why don't you have a ternary merge, or a lot of different merge operations of a lot of different arities? And so the things that this was already observed in empirical terms by looking at examples of structures generated by a hypothetical ternary merge, that if you start generating structures with ternary merges, it both under-generates and it over-generates with respect to the binary merge. So under-generates means that there are certain structures that you want to have, and that will not be possible to obtain with a ternary merge. And the over-generates, it means that it will certainly generate things that you don't want to have. Of course, you can argue that binary merge also produces a lot of things that eventually you don't want to have when you specialize to one particular language. but no, you just things that you don't want to have in any language, which you wanna a priori eliminate. But so let's suppose that we have an n-ary merge, and let's see how that would work. So first of all, that would define for you a magma on a single n-ary operation rather than a binary operation. You can define such a thing in the same way. To start with your set, that generate, and then you repeatedly apply this n-ary merge, and you form. This is the magma that generates the rooted n-ary trees, with leaves decorated by the same set. And now the thing is that if you count the number, so in the case of our syntactic objects, we've graded them by the number of leaves. So you can, the binary rooted trees, you can have any number of leaves that you want. So you can write it out as the disjoint union of the binary rooted trees on k leaves with any k greater than or equal to 2. And if you look at just the n-ary trees, the ones where every internal vertex has n descendants, then this is not the case anymore. No, the number of leaves is no longer true that any positive integers can be the number of leaves of an n-ary tree. The number of leaves of an n-ary tree are only of this form. And so this already says that this structure undergenerates with respect to the it undergenerates with respect to the binary leaves. So you certainly do want to have sentences that only have 2 leaves, and and you cannot have them if you only have a ternary or an n-ary merge with hierarchy. Of course, you could say, well, but if I have both a binary and a ternary, or if I have both, I could do, but then, why do you need the other one if you already have one? So that's one. And of course, there's also another thing that happens. Not only that there's certain lengths of strings that you cannot achieve with an n-ary merge, but also you cannot detect certain kind of ambiguities, of syntactic ambiguities. If I say I saw someone with a telescope, it has 2 syntactic parsing which correspond to these 2 trees, which are different as binary trees, but they would not be different if I had a 4-ary merge. So I would also lose the possibility of distinguishing between ambiguities that I know could be there. So these are like the obvious kind of undergeneration problems that you have if your merge were n-ary with n greater than or equal to 3. But you would also have overgeneration, and there's a slight difference here in the sense that the undergeneration phenomena of a hierarchy merge depends only on the magma of n-ary trees, but the overgeneration phenomena, they depend on the action of merge on the workspaces of n-ary forests. And so these are just kind of rephrasing examples that had already been discussed empirically. But you can see by following what the action of a hypothetical n-ary merge would be on n-ary forest, that now you will be picking n-ary terms in the left channel of your coproduct, and you'll be forming examples of syntactic combinations that don't actually exist in languages. So that was another reason why that excludes the n-ary merge. Okay, so this is another of the list of properties that I was discussing at the beginning in the kind of linguistic introduction to this model. And now the other next property in this wish list is the fact that merge is Markovian. And so this come back to this idea that I was discussing about Markov chains in Hopf algebras. And so normally this merge is Markovian is again assumed as a part of model by saying that your merge derivation at each step should only have knowledge of the current status of the workspace and not have memory of previous ones, which is like a reasonable assumption to make. But the point is that you can actually give a stronger sense in which you can actually prove that merge is a Markov chain in this Hopf algebra sense. So let's just see what that means more precisely. So suppose that I have a graded vector space and a chosen basis for this vector space. This is the case for the kind of combinatorial Hopf algebras in general. So these Markov chains in Hopf algebra, they're usually constructed for combinatorial Hopf algebras, where you have Hopf algebras that are graded connected, and where you have a chosen basis of combinatorial objects like trees or forests or graphs or whatever. So you assume that you start with a linear map on this as just seen as a vector space that preserves the graded subspaces. And the one assumption that you make is that when you look at the matrix representation of this basis in the given of this operation in the given basis of the linear basis of the algebra, the basis of the vector space, then these are have no negative coefficients. Okay. And you also, so if you know that in each of the so for each fixed x, there's some y for which it's strictly positive, at least some for s strictly positive, then you can get a stochastic matrix by normalizing by this. So this is kind of a not completely not completely satisfactory construction, because your rescaling is dependent on where you are. So it's dependent on x, whereas the better kind of case is when you can have not a local rescaling but a global rescaling that will work. And so I'm gonna just call this like a weak form of stochastic of Markov condition. And this stronger form is where again you start with the same kind of data, but now you assume that you have a Perron-Frobenius eigenfunction for this operator that is strictly positive everywhere on all of these basis elements, and then you can just rescale by this Perron-Frobenius eigenfunction, and now you have something that has transition matrices, that form a Markov chain, and this is like this just means that in a sense you are rescaling the basis elements. So you are assigning to your given basis elements a weight that is coming from this Perron-Frobenius eigenfunction, and this makes your in the new rescale basis your operator is a Markov chain. So there is an overall global rescaling still in general, because you might have something where so this is the case where your Perron-Frobenius eigenfunction actually has no eigenvalue 1, but you could have been the case where the top eigenvalue is positive but not equal to 1. So you will have to introduce a global rescaling by that. I'll show you now. But anyway, this is like the condition that's assumed. So in general, the way you show whether there is an eigenfunction is the Perron-Frobenius theorem. And if you start with a matrix that has only non-negative coefficient, not strictly positive coefficient, Perron-Frobenius works well if you are in the irreducible case. So that means that if you you can form a graph that has, this is an n by n matrix, you can form a graph on n vertices, and that has an edge whenever you have a directed edge from I to j whenever you have a non-zero component in this matrix, and that if this graph is strongly connected, so given any two vertices, there is an oriented path that goes between them, then the Perron-Frobenius theorem applies in the nicer form. And you know that there is the spectral radius is the top, the eigenvalue, and well, a priori there could be other eigenvalues on the same circle, but I mean it's of that is positive, and it has an eigenfunction that has all the coefficients strictly positive. And so you can normalize by the Perron-Frobenius eigenvalue, and you can rescale the matrix by the Perron-Frobenius eigenfunction, and then you get something that is a stochastic matrix. So the kind of as I said, there is this theory of Markov chains in Hopf algebra that so the first paper is about this topic is from versus diachronics and Pang and Ram, and yeah, and Pang does a PhD thesis that was about this Markov chains in Hopf algebras. And so in general, these are cases like what I just described, that you have a linear operator that preserves the grading on your algebra, and that in general is of this form. So you start with the coproduct that decomposes terms, then you have some linear map acting on these terms of this decomposition, and then you reassemble them together with the product. And yeah, the simplest example are the one that I said with coproduct first followed by product. And also you can, if you have both co-associativity and associativity, you can form iteration. So you can iterate the coproduct a certain number of times and follow it by the same number of iteration of the product. And that just would do decomposition into n pieces and then a recombination of those n pieces together. And more generally, you can, the examples that have mostly been looked at are where you have a projection in the middle of these two. For example, you project only on a certain degree part of the coproduct. And these are these descent operators that are described here. They're kind of like Adams operations on Hopf algebras. They have to do with Hochschild homology, and they have some nice homological interpretation. Okay, so this is the case, and the main condition, the main Hopf algebra condition, I mean the main Markov chain condition is this fact that you have this Perron-Frobenius eigenfunction. So up to global rescaling, you can rescale the basis so that you get stochastic matrices. And yeah, there's weaker form, just the one where the rescaling is only local rather than global. Okay, so what about our merge operations that we've been looking at? So let's suppose that you fix a certain starting set, which is okay. I guess we'll finish this next time, but yeah, basically it is like you start with your workspace, which has all your collection of lexical items, and that's where you start to applying this dynamical system on that. So you want to show that you have this these Perron-Frobenius conditions are satisfied on such a so there's a subspace on which these conditions are satisfied, for which this actually behaves like exactly like a Markov chain in this. So yeah, I'll finish the system.